Welcome to Peninsula Seniors Out and About. Today we're at the Western Museum of Flight in Torrance for one of their celebrity lectures. Let's go see what Cindy has for us today.
Good morning, everyone, and welcome to the Western Museum of Flight. My name is Cindy Maka, and I'm the director of the museum. In this lecture series, we have been blessed with an impressive array of illustrious aerospace personalities who have been willing to share their experiences with us. It is a double privilege when an illustrious speaker is also a constant and sincere supporter of our museum. Today, we have been blessed with that double privilege. Mike Ciminera, having accomplished many impressive achievements in our industry, is also one of our staunchest supporters. I am personally grateful to be permitted to call him a friend. So now I am especially pleased to introduce my friend, our museum's friend, and aerospace luminary, Mike Ciminera.
Good morning, everyone. It's good to see so many young warriors out there. I'd like to thank you for the opportunity to brief you on the evolution of the F-14 Tomcat. As you can see from this picture, you see the F-14 flying with, guess what, the F-6F Hellcat. Both were known for their outstanding performance and their durability. This speech is dedicated to all of the Navy, civilian, and military personnel that made the F-14 happen, as well as the engineers from Grumman, Northrop Grumman, from Hughes, from GE, you name it, that made the F-14 happen and its lifespan to last over almost 40 years. It's really their story, not my story. I'd like to acknowledge several people and several periodicals that I used to generate this. Obviously, I used my own library and my own archives, but you can see some outstanding books there by James Perry Stevenson, by John Lake, the F-14 Tomcat, by Admiral Gilchrist, by Arthur Reed and what have you, and Bob Kress, who was the chief engineer on the F-14. And I also would like to draw upon the fact that I looked at some articles by Irv Wallen, the chief engineer of Northrop Grumman. Carlos Paez is in the audience. He was generous enough to send me his article on the development of the wing box on the F-14, and some good conversations with Harvey Eidenoff and several other engineers who actually pioneered the development of the F-14. Now I'm going to tell you a story, and what we're going to do here is we're going to go back in time to the post-World War II time period, to the 1947 time period when the XF-10F Jaguar was developed, and then move up to the 60s to talk about the Soviet threat and the VFX competition, which was really that particular group of letters referred to the F-14 competition, and then talk about its capabilities. Now, in the 1967 time period, the Soviets put on an air show every 6 years, literally, and at the Domodedovo Air Show, they shocked the world by flying 5 brand new airplanes and 4 major revisions. This is the Mach 3 MiG-25 Foxbat, which was designed to counter the B-70 Valkyrie. And in this chart, on the lower left, you see the MiG-23 Flogger, which was a variable sweep airplane at the time. And on the top, you see the Su-15 Flagon. Now, that was the beginning of Sukhoi's really major push into be one of the top designing companies in the world today. And down below, you can see the variable sweep version of the fitter. Now, in addition to all the fighters, they had a lot of bombers, as you well know. And flying today is the venerable Tu-95 Bear. This is a high-speed turboprop bomber with a range of probably 6,000 to 8,000 miles. The tough part about this is they keep modernizing it and carry these long-range air-to-surface missiles, which can provide havoc to our fleets if they're not countered. Now let's go back and talk about the variable sweep history. This is a shot of the XF-10F variable sweep Jaguar. This was started in 1947. It morphed into a translating variable sweep wing, and it had an all-flying horizontal tail. You can see that right here on this particular chart. Now, there were a lot of unique features about the XF-10F. It had a translating variable sweep wing. It had 80% Fowler flaps and paddle spoilers. Grumman, in a non-traditional sense, threw all their eggs into one basket, which was not the way we designed airplanes back then. Bill Schwindler, the chief engineer, allowed one new thing at a time, but he allowed the chief designer here, Gordon Israel, to do that. There were too many innovations, but what really happened on the XF-10F is that it proved that the variable sweep wing would lower the approach speed by over 20 knots and almost a 50% increase in range over the F-3H Demon, which was operational in the fleet at that time. That was a conventional swept-wing fighter. Now we move on to the F-111A, F-111B story. This began in 1959 when John Stack proved that you could actually create a variable sweep design and make it work with a fixed pivot. And that led General Everest to move ahead with a commonality requirement. He said, we can design an airplane that could satisfy the USAF needs in yellow and the Navy needs in yellow, shown in Fleet Air Defense, and fly supersonically at low altitude at Mach 1.2 for 200 miles to penetrate the Soviet Union defenses. Well, GD and Grumman won that competition, and they moved out, and Grumman was responsible for the F-111B. Unfortunately, it was canceled. And the reason why it was canceled, it had unmitigated weight growth, and it had really not very good carrier suitability. Although later on they said they could do it, it had very poor vision over the nose, and the weight was just getting out of hand. And the big thing about it, it had no real air-to-air capability. It could not outmaneuver the F-4 Phantom. And as you know, during the Vietnam War, the exchange ratio was about 1-to-1 with the MiG-21s until our tactics and pilot training made it better. But there were a lot of things that were learned from the F-111B, which we took on to future designs. The treatment of base drag at the tail end of the airplane, how inlets interact with fan engines, external store drag and materials, as well as the use of guns and how missiles were really used in combat. This is a picture of the F-111B, one of the flight test birds. It had quite an advanced wing on it. This is shown at about 26 degrees of sweep. It had double-slotted Fowler flaps and a movable variable geometry glove to achieve a lift coefficient of about 2.9. It was not a good carrier suitability airplane in terms of approach, vision over the nose, and what have you. The real drawback was, as I'll tell you later, the Phoenix missiles and the fact they had to operate on swivelable pylons. And what happened is that was a very cumbersome, unreliable, and highly drag-related item. So with all this background, the VFX competition was launched in 1968. The VFX became the F-14A. What the Navy wanted was a fighter for the fighter escort mission. They wanted to fly 500 miles unrefueled with 4 Sparrow missiles and a gun, and they got that. Now, in order to carry that out, that only needed about 14,500 pounds of fuel, but the designers at Grumman had to satisfy the Fleet Air Defense mission, which required over 16,000 pounds of fuel. So what they did is they designed the internal fuel capacity for the Fleet Air Defense mission, right? But when they designed the airplane and they looked at its structural load factor, it was all based on the fighter design gross weight of the fighter escort mission. Some very good thinking went on there. And we were involved, I was personally involved in preliminary design at the time, and we did over 6,000 different studies of different airplanes. And these are just some pictures of them, the 30360, the 303C, which had integral engines or engines side by side with a low variable sweep wing. Then we went to the 303D, which had engines close together with a high variable sweep wing, and the 303F, which ended up to be about 5,000 pounds heavier because of the demands of carrier suitability to satisfy the Fleet Air Defense mission and other constraints. And the competition responded in almost the same way. North American Aviation came in with a fixed wing design, and Vought, along with McDonnell Douglas, came in with a variable sweep. And one of the things that happened is that through George Spangenberg in the Navy, he said, you go look at the Vought design after we won it and take a look at their maneuvering slats, which we adopted on the F-14. So the winning design was the so-called 303E. Now, and this is the first mock-up that was built. One of the things you can see quite dramatically is the tremendous vision of the pilot and the radar intercept officer. For an air-to-air fighter, you had to have 360-degree visibility and excellent vision over the nose as you approach the carrier. That they put into the beautifully designed shape of the forward module of the F-14. It had a single vertical tail initially. The Navy said, no, we don't want that. We want double vertical tails because of single engine out controllability, and we got rid of those ventrals that were used for directional stability at high speed, so we simplified the airplane. Now, when we set up the genealogy of the F-14, this is where the conservatism and the design philosophy of Grumman came in. They said, look, we're only going to take one thing at a time. So the first thing they designed was a new airframe, the structural heart of the airplane. That's what gave the airplane its longevity and its life and its ability to handle the strike attack missions, as I'll tell you later on, and what have you. Then we would jump to the F-14B with a new engine, and then to an F-14C with advanced avionics. Now, I have to tell you, it really didn't turn out that way because of a lot of the funding problems that occurred. I won't go into all that, but it did happen in terms of an F-14A, an F-14B, and an F-14D, which I'll tell you about later on. Now, there were a lot of white rabbits that made the F-14 happen aerodynamically. And I'm going to just briefly mention them. There were 7 of them. We thought we would get 4. But these were the white rabbits, along with the use of the titanium structure and the wing center section that made the F-14 a reality. We start with a variable sweep wing. We start with the fact that the wing was always sweeping automatically. The pilot eventually learned that he didn't have to move it. The computers took care of that, which I'll tell you about. The wing pivot selection was ultra critical in terms of minimizing trim drag. And we used deflected leading edge slats and flaps for both takeoff and landing, but even more importantly, for subsonic, high maneuvering, high G aerial combat, which I'll show you in some of the slides. We incorporated glove vanes, which I'll tell you about, and then we went to a widely spaced nacelle concept. The engines were not close together, they were moved far apart, and we used something called weapons rails in order to mount all the stores on. Now, when we look at the variable sweep wing, at the time, it was the only solution that really satisfied the Navy's requirements. First, they wanted to go Mach 2.4. That required minimal cross-sectional area and a very thin wing. So when the wing was back at 68 degrees, you had a very small thickness-to-chord ratio. To satisfy the long-range escort mission of 500 miles, you had to cruise out 500 miles on internal fuel. So you had to have a very high aspect ratio wing with very high lift-to-drag ratio. And at the same time, they said, you know, we want you to do the Fleet Air Defense mission and land back on board the carrier with 6 Phoenix missiles and 4,000 pounds of fuel. That was roughly 10,000 pounds of weight at the time, which was unheard of. Now let's talk about the next white rabbit, which was automatic wing sweep. Now, this is the first technical chart, so bear with me. We have a few of them in the briefing. On the vertical scale, you have relative lift-to-drag ratio. This has been declassified versus Mach number. And what you see then is the variation of lift-to-drag ratio with various wing sweep angles. And the dotted line shows how the Mach sweep programmer, through a central air data computer, which was highly redundant, actually swept the wing to maximize lift-to-drag ratio for the particular performance that was required. Now, you see the F4 and the MiG-21. So the L over D of the F-14 was about 15. The F-4 Phantom, depending on the version, was between 10 and 10.5, and the MiG-21 was about 7. So there you can see the tremendous difference in terms of lift-to-drag ratio, which related to turning performance that we were struggling to get in that time period. The next point was wing pivot selection. Now, we're getting a little deep technically here, but you got to stay with me. What happened is that on the F-111, when they developed the pivot design, the pivot was located fairly close to the center line of the airplane. As the wings came back, the center pressure, the center of lift, moved aft, which caused a tremendous change in trim drag and a lot of drag. On the F-14, they moved the pivots outboard, almost 3 feet more on each side. And what happened is when the wing swept, less of the wing actually swept back, so the center of pressure didn't move as much, and guess what? They had less trim drag. And this was all part of building the performance of the airplane. Now let's talk about all the control surfaces. The F-14 had a lot of them. It had a glove vane, which I'll tell you about. It had the wing in the forward position, had leading edge slats and maneuver flaps and an aux flap. And those flaps and slats had intermediate positions for maneuvering. It also had an overwing fairing and an airbag, which I will tell you about, which is very interesting in the next chart. Now this happens to be a picture of the F-14B at catapult at mill power coming off the angled deck. And what you can see here very clearly, if you see that dark area in the center of the airplane, that's an airbag. That's a canvas airbag that was treated, that actually inflated and deflated because the wing sat on top of the fuselage. And on top of the wing, there was an overwing fairing with titanium fingers. So as the wing swept, the bag expanded and the fingers collapsed down, so you had almost a near contour on top to minimize drag. Very interesting concept. Now, when we talk about wing loading on an F-14, you have a totally different translation, so to speak, because classically the wing area shown in white was on the F-14 was about 565 square feet. But because the nacelles were widely spaced, it was literally a lifting body. So when the wing lift gave out, the body was still lifting. So the true wing loading in combat for the F-14, when you had instantaneous turning and very tight turns in aerial combat, was more like 44 to 48 pounds per square foot as compared with the F-4J and the MiG-21, which were higher. Another secret of the design and the good thinking by all the people that evolved the design. Another technical chart. This shows the impact of maneuver slat and flap on turn performance. Here you see relative turning capability on the vertical scale versus angle of attack. And on the lower portion, you see the F-4 and the MiG-21 running out of gas between 12 and 16 degrees. Well, when the flaps and the slats were extended, you saw the F-14 going all the way out to 24 degrees angle of attack with almost twice the turning capability. And this was one of the secrets of how this airplane, which was very big, could literally turn inside of a MiG-21 and an F-4 in aerial combat. A lot of people didn't know that. Now we get to something called glove vanes. Now the glove vane is shown here on the right. Now this picture on the right, let me orient you. You see the inlet right there, and you see the landing gear, and you see that triangular shape. It comes out about 15 degrees. Now that was originally put in there for the air-to-ground mode, because what would happen is that as the airplane was diving, that would come out and create a lift force forward of the center of gravity that would counter the forces that were being put on the horizontal tail and lower the structural loads in the rear fuselage. And it was a tremendous load alleviation device, but also it was used for supersonic turning and in subsonic combat. And here you can see again, this is the last technical plot. This is relative turn capability versus Mach number. The dotted line is the F-4, and there you can see the F-4 with the vane retracted and the vane extended, turning right at the structural limit. In other words, the F-14 could pull 7.5 Gs at Mach 2. Imagine, at Mach 2, with a constant NZW product, but depending on the weight, it could pull that. It's really quite remarkable what was in the airplane. Now we get to the next set of white rabbits, and these are the widely spaced nacelles. On the left, you see the orientation of the airplane from the front. You see the widely spaced nacelles, and from the rear, you see it with the convergent, divergent nozzles, either open and closed. And I just want to mention a few seconds about the two-dimensional external compression inlets and the convergent, divergent nozzles. This was a very simple design. The TF-30 was a bomber engine, and I was telling you, and it needed very clean air, so we couldn't turn the air a lot. So we had to have a straight-through flow, and with the two-dimensional inlets, they actually positioned the shocks outside the inlet so nice, slow air could get to the compressor face. That was done very effectively. In the back, Remember I mentioned on the F-111B that base drag was very critical. This is where the air breaks away from the nozzles and causes drag. On the F-14, we did not have that problem because of the convergent-divergent nozzle. They were very clean, and you can see what happened. Now, in that channel between the nacelles is where we put all the stores. And the secret of this was in something called a weapon rail. Now, the weapon rail, each one weighed about 1,000 pounds. It had its own internal hoist, and you could literally bring up from the bowels of the carrier a weapon rail with a Phoenix missile on it, which weighed 1,000 pounds. You could hook 4 of them on the bottom of the F-14 in less than 20 minutes. You could rearm the airplane. Then you could land, you could put bombs on it, and what have you. And what happened is that, as opposed to the F-111B, where they had an internal bomb bay, we had everything external in the channel in a low drag installation. And what happened is when we designed the airplane for all the structural load factors and what have you, we didn't have to carry that weight penalty. That was an overload condition, so it saved a lot of weight. And on the right here, we see a picture of the F-14 with 6 Phoenix missiles and in a vertical climb, and you can see the very low drag installation with the fairings in front of the missiles. Now we get to a favorite subject of 2 of my colleagues in the back, Carlos Paez and Harvey Eidenoff, who were really the structural pioneers in many ways on the F-14. Carlos was responsible in large part for the design of the wing box, and Harvey was responsible for the fatigue aspects of the airplane, and I say that with a great deal of respect. Let's take a look at the structural components and orient ourselves in color. In blue is aluminum. Roughly 40% of the weight, that is to say the airframe manufacturer's planning report weight, was aluminum. The green was titanium. That was 6Al4V titanium. That was almost 25%. You had boron epoxy used for the first time in the horizontal tail, a long way from the center of gravity of the airplane, where weight was very critical, and and that saved about 300-400 pounds, and the rest of it was steel. Now, one of the things that happened on the airplane was the titanium wing center section that was really the heart and soul of the airplane. What Grumman did, they formed a titanium committee several years before the actual award, and they began to study the use of titanium that would be key in keeping the structural weight down to a low level, as I'll show you in following charts. They bought the electron beam welders shown in the background, 3 of them from Boeing, from the supersonic transport program. They ended up creating an 80,000-foot, unique in the world, titanium welding facility. And what was created here after many, many, many months of testing and article testing was a titanium wing box shown there in the foreground that is as follows. 22 feet long, weighed about 2,000 pounds, 900 pounds less than an all-bolted steel box. It carried go-home fuel in it. It had 35 subassemblies that were put together with 70 wells, all done in a vacuum chamber with wells from 1/2 inch to 2.5 inches thick. Imagine what had to be done to put this together. And it was probably one of the most unique structural things done in the world at that time. Lockheed was working on titanium, but they were using it for the SR-71. That was a black program. The other part of this was the thing called fracture control and non-destructive testing, because normally with this type of structure, the Navy did not like welded structures in primary structure. They wanted bolts, things that you could hold on to. So what had to be developed was a whole series of tests and analytics to determine that each one of those wells was solid. And indeed, the first 36 of those boxes that were built were tested to 115% of limit load, just to prove to the Navy that they worked. And it worked extremely well. Now, this chart may be a little hard to see, but what you see here in the upper portion is the F-111B model, and in the lower portion is one of the earlier F-14 models. Those used to be in my office, which we used for giving briefings. But you can't see it too well, but in the upper portion, the F-111B had a crew escape module, it had a bomb bay, it had the gear retracting into the fuselage, and the wing, when it swept, actually cut the fuselage bulkheads. Whereas on the F-14, the landing gear was external to the fuselage. It had no bomb bay. They had tandem seating. So you saw nice, long longeron runs from the nose to the tail on the F-14. And when you added this all together, you found out that the F-14, in terms of its primary structure, because they were about the same size, was almost 10,000 pounds lighter. And when you looked at it very carefully, you saw the use of titanium. Now, the F-15 also had titanium in it, about the same amount, but the F-4 only had about 9%. You had the Mach sweep programmer. Remember I told you how the wings swept automatically. It limited the wing bending moment that we had to design to. Electron beam welding saved considerable weight in the airplane versus a bolted structure. I talked to you about the ejection seats, the weapons rails, the landing gear, the wings on top of the fuselage, the straight flow-through ducts, and the boron epoxy tails. All of those added up to almost a 10,000-pound reduction in the airframe weight. And that was the key that allowed the F-14 to grow over, in terms of capability, over 40 years. This is a picture of the glove area. I showed it to you before, but there you can see the wing in the oversweep position at 75 degrees. That's the wing glove there, and you can see the landing gear that retracts into the glove as opposed to cutting primary structure. Now let's talk a little bit about the engines. This is a very interesting and somewhat sad story, and yet it had a happy ending. It took a little while to get there. What we see on the upper picture is a picture of the TF-30 engine, which was inherited from the F-111B. And we thought we could use it in the fighter because it had already been developed. In the lower portion, you see the F-110 engine, the General Electric F-110 engine, which was used in the F-14A Plus and B version. Now, you really had 1960 versus 1980 technology. The TF-30 engine was essentially a bomber engine. It suffered from compressor stalls because you have to remember the F-14 was turning at very high angle of attack, very tight turns. The pilot wanted to slam the throttle. That engine could not tolerate that at all. And we found that out very sadly as we got into operational service. So they had to put operating limitations on it. It still was able to perform very well in the AIM-ACE eval test in '73 against the F-15, where they had a 2-to-1 advantage over adversaries because of its tight turning capability subsonically. But it wasn't until 16 years later that the final engine got into the F-14, where the pilot could literally take the throttle and slam it back and forth with no problem at all. And there you had an airplane with very high thrust to weight who could compete with almost any airplane. And you can see the difference in thrust. The thrust to weight on the top and the bottom has to do with the thrust to weight of the engine. You can see almost a 50% increase in thrust to weight over the TF-30 versus the F-110. And by the way, it was 50 inches shorter. Just an incredible change in technology. Now we're going to talk a little bit about the weapons system. The F-14 would not be the great airplane that it was without the AWG-9 radar that was developed by Hughes Aircraft. I say that with a great deal of sincerity because I worked very closely with those folks. The AWG-9 in its day was at the top of its class. It had a very large antenna. That's one of the flight test airplanes. It had an excellent fire control system in it, and the Hughes was able to take almost 700 pounds out of the AWG-9 to put it in the F-14 from the F-111B, and also reduce the amount of volume for all the boxes from 46 to roughly 30 cubic feet. And the AIM-54 missile down here was about 1,000 pounds. I mean, it was a long missile, very, very big. And the capabilities were really, really remarkable when you looked at them. First of all, in the pulse Doppler mode, it could detect targets in excess of 190 kilometers. Actually, it was much farther than that. It had the ability to track while scan 24 targets at a time. You could not do this with the Phantom. And it had the ability to launch multi-shot track while scan 6 Phoenixes. And I'll show you that in one of the test sequences. And the later versions of the Phoenix also had electronic countermeasures capability because the threat was actually changing. And it had the ability to handle the Phoenix, the Sparrow, the Sidewinder, and the internal gun as well as internal weapons. Now this is a very interesting chart because when you look at it, one of the unique things that happened on the F-14 is when they put the F-14 out there with the E-2C, they began to develop a total strategy for air defense. Remember, they both came up separately. They put them together and they could range the E-2 way, way out beyond the 400 miles. You could have F-14 sitting on the deck getting all of that information shown on the tactical information display before he actually took off. That was the beginning of what we call network-centric warfare on the F-14 E-2C. Tremendous capability. Now, I'm not going to dwell on this chart. This shows all the radar modes, but I thought we would have a few electronic folks in the audience. Just draw your attention to the fact, to the yellow. In the pulse Doppler search mode, the range of the F-14 was 2.5 times that of the F-4J. In the range while search mode, the volume was 15 times greater. And the difference, you realize the Sparrow was a semi-active guided missile that had to be illuminated by the radar at all times. With the Phoenix missile, you could launch it from as far as 60 miles away, and it had its own active terminal seeker, so it went way up and over and came down at over Mach 3 and could take out a target at 60 miles away. You could literally outpunch anybody at the time. This is a picture of the pilots and the RIO operator in the F-14A. On the left, you see a classical heads-up display. It's hard to see, but he had a horizontal and vertical indicator group displays on the left. And on the right, the RIO had the detailed data display for pulse Doppler search and a tactical information display, a big screen that showed the whole radar world. Now, the big thing about the F-14, you can see the visibility. In air-to-air combat, that guy in the back seat was looking all the time in terms of seeing where the enemy was. It really meant a lot in air-to-air combat. This is a look at the various air-to-air weapon loads. There are many different types of configurations. One of the classical ones was to go down here, second on the left from the bottom, was 4 Phoenix, 2 Sparrow, 2 Sidewinder, and a gun. Nobody could bring that kind of capability into a foray. And what the F-14 really wanted to do was take you out at long range. But if he had to get close, he could maneuver with the best of them. This is another picture, again, a larger one of the load with 6 Phoenix. Now we get to the F-14B. Remember I said the F-14B took about 16 years to mature. Remember, the plan was to only build 67 F-14As, including the prototypes, and then go to the B. Unfortunately, there were tough financial situations. And way back in 1971, Secretary Packard said, "We're not going to spend the money on it. You live with the TF-30." And the Navy said, "Yes, sir." But they were not happy about it. So they kept pushing and pushing and pushing. Eventually, after the number 7 flew in 73, they had the Super Tomcat fly with a derivative fighter engine in 81. And then eventually in 1986 and down to 91, the F-14B entered service. It was a magnificent airplane because it finally reached the right thrust to weight for its size. And as I say, the pilots had literally Bodie-free performance. They could slam the throttles back and forth with no problem. And this is a picture of the F-14B in a strike mode with 4 Mark 83s. Now, the interesting thing about the weapons rails is they could handle a 2,000-pound bomb and also the big GBU bombs, which I'll show you in the next charts. Because what was happening now, as we're into the late 80s and into the 90s, the technology was reaching the point where we could now really put into play a strike fighter, which I'll tell you about in the next charts. And here it is. This is the ultimate F-14. It was originally the C. It ended up being the D. But what it had in it was an APG-71 radar, again developed by Hughes Aircraft. They took pieces of the AUG-9. They took the radar out of the F-15E, the APG-70, and they created a wonderful system called the APG-71. The Navy said we want new computers in it to give us a bus architecture that could handle anything. And we put the new engines in it. Unfortunately, they only built 55 of them, but I had the privilege of debriefing the crews when they came back from Iraq in 2006, where they were the only ones that could provide the long-range strike that was needed in the Iraq War in the early days because we couldn't get the fighters to operate from the bases then, and the F-14s did that job. This is a picture of the advanced cockpits in the D that had a brand new front cockpit with a multifunctional display. It had a redo of the aft cockpit for the RIO, again with a new functional display, and it had a chin-mounted infrared search and track as well as a TV dome in order to enhance its air-to-ground capability at night, etc. And this was the final loadout of the airplane. I told you a lot about the Sparrows and the Phoenix missiles. Over here on the right, you see the Lantern pod, the TOPS pod, and the guided bomb units, the GBUs, which are used a lot today by the F-15E and a lot of the top airplanes. This is just one more picture showing the loadout versatility of the airplane and the uniqueness of the weapons rails. Here you see a TARPS pod with another jammer pod located forward of it with Sidewinder missiles and what have you. One small mention of the Tomcat 21. The F-14 was not over. In the late 80s, we started working on even an advanced version. And the only reason why we could do that, and I won't dwell on this, was the fact that we had a good airframe that could grow. So we were looking at an all-digital fly-by-wire system, new engines, new avionics, greater weapon carriage capability. You could see the glove area there was much larger, and there were many, many versions of that. And we even started to look at stealth adaptation to the airplane. But unfortunately, that did not happen. And then we get to a sobering thing called cost. You remember way back on the F-111B chart, one of the things I didn't mention was cost. Well, airplanes sell like chickens. They sell by the pound. And here's a plot of flyaway price versus takeoff gross weight. And on the lower level is what was proposed in constant $75. Some of you remember 1975. Then if you went to $84, it pitched up. But if you put inflation in at the time, you saw the real prices of the airplanes. Now, obviously, they're rate-driven. You could see the difference of the F-14. But the F-14, remember, had almost 3,000 pounds of avionics in it as compared to the smaller airplanes. So obviously, it was going to be more expensive. But in those days, they sold by the pound. The bigger the airplane, the more expensive. That's what it was. Now, we're getting near the end now, and I'm just going to say something in perspective, that it was the first operational air superiority with a fully automatic variable sweep wing. It was quite a unique capability. No other airplane has accomplished that. It had multiple and simultaneous missile guidance and look down, shoot down at extremely small targets. And as a strike fighter, it could carry 10,000 pounds of ordnance hundreds and hundreds of miles. Depending on the mission, it could reach out almost 1,000 miles. It's really quite remarkable. And it did not lose the good carrier suitability on the lower left here with a V approach of 135 and a V stall of 115 knots. So we're getting to the summary now, and again I want to say that a great deal of leadership and a great deal of credit goes to the Navy uniform and civilian leadership. I can't mention all the people that I interfaced with, but I did know Tom Connolly, Admiral Tom Connolly, and George Spangenberg, as I know some of you in the audience knew, who were really great leaders and fine engineers and visionaries who made the F-14 happen. The design team led by Mike Pelahak, he surrounded himself with the best and the brightest. Irv Walland was head of Aero. Irv is here. And Carlos Payos did the titanium wind box. And Harvey Eidenoff was in charge of the fatigue. So he surrounded himself with the best people. And Bob Kress was the chief engineer. Wonderful things. It fulfilled all its mission roles over its life. Personally, it could outpunch anybody. It was like the SR-71. You couldn't touch it at long range because the Russians were actually afraid of it. They stopped flying the MiG-25s out of Baku over Iran in the early days because the F-14 could intercept it. And it retired at the peak of its performance. The F-14Ds were still actively being deployed, and their role is now being filled by some excellent airplanes, the F-18EF, the F-35, the F-15E, and the unmanned tactical systems, which are coming along. So ladies and gentlemen, that's the end of my story. I'm going to now move into a DVD, which you'll find very interesting. It shows test sequences that you've never seen before, that have never been seen, because they are all old films that were made when we actually retired the airplane and showed it to the retirees. The first things that you're going to see here are some of the Design 303, and these are some of the configurations that I showed you in the briefing. These were the preliminary design studies that I personally was very involved in. And there's the single-tail mock-up, and with the wings swept, and there it morphed into the twin-tail mock-up, which I told you about. This was a fully powered mock-up, by the way. There you can see the two-dimensional nozzle. We won the competition. There's Mike Pelahak, and there's the mock-up out on the field. This is the engineering mock-up and manufacturing aid called the EMMA, which we used to actually figure out how to build the thing. And that was quite an instructional thing. You can see the various sections coming together. This is the bearing that's being put into the platter. Each platter on the F-14 was 2 inches thick. These are all the tests that were done to prove out the electron beam welding techniques. And you can actually see some of the welding going on right there. This is the mounting of the boron skin on the composite stabilizer, which, by the way, we couldn't break. We tested the 4 times life. We couldn't break it. This is a full-scale wind tunnel test, which I'm sure Irv remembers very clearly, and some of the flow visualization tests to look at the drag and flow fields. This is the a full-scale inlet test, just to see the way the air actually flowed coming in. This is the fuel slosh test. Now you can see the wing box that had the fuel. This is the hydraulic systems simulator. I was talking to a gentleman here that understood a lot of that. And we actually used a PSI system. This was the windshield tests and rain removal tests, which we did. We established a systems integration test stand out in California, where we actually took all the equipment and put it together in its actual confines of the fuselage, where we looked at vibration and temperature. These are the gun firing tests using the M61 cannon. I can tell you an interesting story about that. These are the early tests on the TF-30 with the afterburner. And there you can see the CD iris opening up as we went to maximum afterburning power. These are some shots of the flight test. This is the second flight of number 1. We lost this airplane because the backup hydraulic system did not work. And I can explain that to you a little bit. You can see you can't see it too well, but the fluid was leaking out. They had roughly 1 second to eject, and they did. Both pilots survived, and they flew again another day. This is number 2, first flight with an all-steel hydraulic system. They made us take out the titanium. We eventually put it back. This was 1X doing very high alpha tests, and in the upper right there, you couldn't see it, but it actually had an asymmetric wing sweep test. We could actually land the airplane with one wing at 60 degrees and one at 20 at about 170 knots. That was demonstrated on a field. These are high angle of attack tests. There you see the controllability of the airplane at very high angle of attack. That's Joe Burke taking number 7 to over Mach 2.4. And this is these are the catapult tests that were done at Lakehurst, and this is the first carrier arrestment that was conducted, and they found out they had a winner in terms of its airplane handling qualities. These were gunfire tests at high altitude. And this was the production line. At one point, we were building as many as 6 a month, 72 a year, and building 10 wing boxes a month coming out of that titanium facility. This is the production line out at Calverton. This is the 6-on-6 Phoenix shot. that was conducted. Now, I guess 5 out of the 6 hit their targets. The 6th one, they say, probably would have gotten it, but it did miss. But they had subsequent other multiple shot targets that worked very well. This is the Super Tomcat flying with the derivative fighter engine. This is the one where we got like a 60% increase in time to climb to altitude. Absolutely remarkable performance. And this, of course, is the F-14D, which was the ultimate strike fighter that I told you about. And there you can see the engine installation. These are pictures of the F-14s being deployed. They kind of speak for themselves. The nice part about it is, as a big airplane, it had an oversweep of 75 degrees, so the spotting factor, the silhouette on the deck, was actually less than the F-4. It was really quite remarkable, or comparable to it. There they are in echelon configuration. Now there's an ACM shot with the wings being forward. Now remember, the pilot in ACM did not touch the Mach. It was all done automatically. The wing positioned itself through the central air data computer. It knew exactly where it was: altitude, temperature, pitot, static pressure, total pressure, Mach number, and it moved that wing. The pilot did not have to touch that wing at all. Now, these are just a couple of films that it was in. There you see Kirk Douglas, the final countdown. In one scene, he says, "Launch the F-14 Tomcats," and there you see some pictures. And of course, it was the sweetheart airplane in Top Gun, which is coming up next, which many of you and your children have seen. And it was really a wonderful picture. In fact, the head of VX4 is a good friend of mine, did these flight sequences against adversary airplanes. And these were really ACM shots that were taken. Now, of course, with Tom Cruise, he was not in the cockpit at the time, obviously. Now, this is the fighter fling, which really got involved with a lot of the tactical development on the airplane. These are wonderful shots. There's shock waves forming, some of the pictures with multiple loads, arrestments, ACM shots, multiple takeoffs. Again, some more ACM shots. You're going to see some low altitude capability. Now there you see him going into a turn with the Mach sweep program and working. You see how fast it moves? The wings swept at 7.5 degrees per second at 1 G and 4 degrees per second at 7.5 Gs. The F-111 only swept 3.5 degrees at 1 G and could not sweep under load. So that shows you the difference in capability. And these were some of the last formation shots that were flown. Here it is on arrestment. That was a good landing. Remember, it was qualified to land at almost 26 feet per second. Imagine dropping at 20. When you touch down on a transport airplane, it's less than, it's about 2 to 3 feet per second, so it's remarkable. These are the various squadrons, and you're going to see some low altitude shots here. And there it's dropping GBUs. And it was retired in 2006 after 37 years of service. I think that's about it. Are there any questions? Yes, you asked the question about the pivot point. The pivot point on the F-14 was 8 feet 11 inches, almost 9 feet from the center line. The F-111B was 6 feet from the center line. Were there any accidents for the wings failing to deploy? I don't believe there were any operational accidents due to the wings failing to sweep. There were, I think, over 30 years of service, the driving actuators that actually moved them failed twice, which is remarkable. And also the airplane, as I mentioned, if one of the actuators failed and one wing, let's say, was left back at 60 degrees and one came to 20 degrees, the airplane was fully controllable. In fact, they had to demonstrate to the Navy in 1985 asymmetric landing. I didn't show you the chart on it. I have it hidden. But basically, they could land the airplane, I think, at about 175 knots. Now, if it failed at more forward positions, the speed got less and less, but it was controllable. And Chuck Sewell, the chief test pilot, demonstrated that in 6 flights. The question is, how long did the design team stay together for all these changes? That's a very excellent question because, as you know, when you design an airplane, it takes 5 to 7 years to make it happen. Irv knows this very well, very well. He's smiling. But let me just step back. We actually had about 1,800 engineers at the time of award working on the design of the airplane. So after the go-ahead, we held them together for about, I would say, about 6 years. Then they began to change, right? Change slowly, because the airplane was out of development then. It's absolutely critical during the development phase, which can last maybe 2 to 3 years, that you keep that design team together. It takes time to build them up, and it takes time to get them to work together as a team. Nothing has changed in the industry. Yes, they use CATIA 5 and they can design in 3 dimensions. They don't build wooden mock-ups anymore, but you still have to have that team together to talk and to discuss things. So I don't know whether I answered your question, but I would say about 6 years. Was it ever employed in combat? I don't believe it was. It was deployed operationally. They used Sidewinders and Sparrows in combat against the Libyan airplanes. The F-14 shot down 4 of their Su-22 fitters. But it was employed totally over its lifespan. In other words, when they were in the air superiority fleet air defense mode, Phoenix was always on board. And they kept developing it. Remember, the AIM-54A became the AIM-54C, which was a very unique system. And but it was not employed. But I will tell you that the adversaries knew what it could do. I mean that sincerely. Any other questions? Who did the flight control system? Well, remember the F-14 was not a fly-by-wire system. It was the last of the old-fashioned cranks, hydraulic servos and what have you. You had Honeywell involved. You had, trying to remember all the names, but all the classical names that worked. Moog was involved. Various companies like that. Yeah, and the interesting thing about the F-14 and all their systems, even the landing gear, we had people that knew as much about the landing gear as the landing gear makers. We had people that knew as much about the design of flight controls and flight control philosophy, especially from the F-11 Tiger, which, as you know, was a Blue Angel airplane. It had tremendous controllability. All of that expertise was ground in. So when we laid down the specifications and the requirements and worked with the subcontractors, they were designing to our philosophy, not their philosophy. There was an interchange, but we had that capability. Not to take anything away from them. What you asked about was, in the design phase, how did you account for all the ordnance? This was a very tough issue because on the F-111B, the Phoenix missiles were inside the airplane, 2 of them were, and they put Phoenix missiles on swivelable pylons, as I told you, which was very heavy, very unreliable, very complex, and had high drag. What we decided to do, not me, we left the wing completely clean. Nothing touches on the wing because of the controllability aspects and the way we designed it for maneuvering. What we did is we selected a configuration that had widely spaced nacelles, and we put them in this channel. And instead of designing the structure to carry these internally. They were carried externally, but they were carried on streamlined weapons rails. So when you actually calculated the loads and the structural load factor, we didn't include that in the design. In other words, it had to carry it, but the fighter design gross weight was based on carrying 4 Sparrows plus the gun. When we went to the Phoenix missile design, that was really a heavier configuration. So we didn't penalize the fighter. The reason why we could carry them so effectively is that they were in low drag installations. Before that, most of the stores were carried on the wing in very high drag installations. Remember, the F-14 could go supersonic with 4 air-to-ground stores in the channel. Imagine going supersonic with 4 air-to-ground stores in the channel, not necessarily with anything mounted on the glove pylons, but it had that capability. No airplane could do that at the time. Now, obviously, today they can. So that's how we did it. It was a wonderful ingenuity by so many people, really. It was just a tremendous achievement. And remember, we learned from the F-111B. Without the F-111B, we wouldn't have been this smart. In the chart that I gave you, the F-111A ended up being one of the finest aerodynamic airplanes in the world. Remember, the F-111A through the F could go at Mach 1.2 on the deck. No airplane in the world can do that, right? But they had problems with base drag, they had problems with external stores and cutting up the fuselage. But if Grumman had not worked with General Dynamics and learned, we wouldn't have not been able to apply those lessons to the F-14A. We maybe would have gotten there, but it would have taken a long time. So you have to give people credit. You have to give GD credit. You have to give everybody credit. You never do anything alone. Any other questions? Yes, Bob.
How active were the F-14 in the Vietnam War?
The F-14s were, that's a good question. They provided air superiority coverage to our carriers in the Vietnam War in the 75 time period. In fact, they provided the MiG-21s could not come up as we began to withdraw because of this. They created a screen, and did they play a major role? I don't think so, but they were deployed in the Vietnam War. They just got in at the end, yeah. Okay, well, listen, it's been a great honor and a privilege talking to you all, to all the young warriors in the audience. Thanks very much.
Thank you for watching Peninsula Seniors Out and About here at the Western Museum of Flight and Torrance. I'm Betty Wheaton. I'll see you next time.